Okay, so recall, this is, I promise, this is how I planned on doing this next thing, but it's also kind of funny because this is a very common mistake from the exam, okay? That the log base b of any number b is always equal to 1, right? And this is literally, I think, the same thing that happened in your exam. So b to what power equals b? Well, b to the first power equals b. So this is for any number, right? So, log base 3 of 3 is 1. Natural log of e equals 1. The common log of 10 equals 1, okay? Wear a wig every day next week. I don't have that many wigs. I'm running out. I'm running out of new wigs. We could get old ones, though. Here's what I will do, though. I might shave my beard next week, and I might give you guys a very special shaving. There's a lot of cool styles that you can do when you shave your beard. If you're good. All right, so we were doing example 2. And we were on part E. So 5 to the x plus 2 equals 4 to the x. Okay, so if they had the same base, right? If these were both 4s, we'd say, okay, the exponents have to be the same. But they're not both 4s. And there's nothing we can do. Well, there are some things we could do, but nothing you want to do that can make these bases the same. 5, not a 4. So we're going to do new strategies today. Okay? Specifically, we're going to use something called a logarithm. Now, you may not have heard of logarithms, but logarithms are the inverse functions for exponents. So, let's say I want to inversicize, it's not a word, but if I want to get rid of this exponential on the left-hand side, let's just take the log of both sides. And let's say log base 5. And any base works. Log base 5 is my preference. Log base 4 is also a good choice, but any log works. Okay? So, we're going to take log base 5 of both sides and see what happens. Just like we can square both sides, subtract 5 from both sides, multiply both sides, we'll take the logarithm of both sides. Works for any one-to-one function, by the way. So we have the log base 5 of 5 to the x plus 2 equals the log base 5 of 4 to the x. And now we just simplify. And you might say, Jason, this looks way worse. But no, it's better. Have a little patience. Have a little trust. Trust that I would never lie to you. Okay? So, log base 5 and the exponential function, these are inverse functions of each other. They cancel each other out completely. These are not inverse functions of each other because they have a different base. Okay? So the left-hand side really does just simplify to x plus 2. But I want to review why it simplifies to x plus 2. Right? So we have properties of exponentials. Right? Properties of exponentials says that this exponent comes out in front as a coefficient. This comes x plus 2, the exponent comes out in front, times the log base 5 of 5. Right? And the right-hand side has the same thing. The exponent comes out in front, x times log base 5 of 4. All right. So now this is really nice because this over here, right? Log base any number of itself is always 1. So this right here is just 1. So we're left with x plus 2 equals x times the log base 5 of 4. And this is just some ugly number. So it's not as nice as before, but it's not that bad either, right? We have a linear equation. No more exponents. No more exponents, okay? So we just solve this. It's a linear equation, right? There's only numbers and x's. So we get all the x's on one side, all the numbers on the other. So these are combined, so we need to move this over. And we need to move the 2 over 2. So we're going to get x minus x times log base 5 of 4 equals -2. Now all the x's are on one side, all the numbers are on the other side. We still have to, well, we'd like to combine these if we can. We have a trick. We have a trick for this. We've done it a little bit before. We're going to do it again. We're going to factor the left. Okay? If we factor out, because we can't divide both sides by log base 5 of 4. Right? If we try to divide both sides by this log, well then this x just gets it. The only way to solve for x is to factor the x out and divide by what's left over. Okay? So we factor out the x and we're left with 1 for this guy. Minus factor out an x, we're only left with log base 5 of 4 over here. And now we can divide by this coefficient and get to our answer. So it's not the most beautiful answer. You may be a little disappointed that this is your answer. But our answer is x equals -2 divided by 1 minus log base 5 of 4. Whoa! What an answer! So the problems we're doing today are going to be a little bit messier and a little bit more difficult than the problems we did on Tuesday, earlier on in the section. Okay, so strap yourselves in, tie your socks on so they don't fly off, and wrap your sandals up real tight. And again, you could type this into a calculator using the change of base formula to get an approximation, but my rule of thumb in most math classes is to give an exact answer whenever possible and give approximations for applications. If you're, hey Bella. So like, and sometimes for applications I'll specify, you know, like round to the nearest thousandth, round to the nearest hundredth, but sometimes in applications it's just obvious. Like for example, never mind. I'm not going down this road. This is too mean even for me. All right. Part F. Okay. Let's do another one. 2 to the x equals 3 to the x. So I want someone to look at what we did in the last problem and give me a guess on what's our first step for F. Look at what we did in E and do F. Okay? Someone give me something. Someone give me something. Y'all are busy, too busy memeing to give me the answer. We'll get that answer, and then we'll be done even quicker today. Or we'll just sit here forever. Even a guess. Looking at what we did for part E. Because the hint is that it's essentially the same exact thing. The question, Gabe, is what do we do to start part F? It's going to be something similar to what we did for part E. The x is going to come out in front, yeah, but we have to use logarithms first. But that's exactly the idea. That's where we're going. Good. So we're going to take the log of both sides so we can use properties of exponents and bring the x out in front. So we can use any log we want. Log base 2 is a good choice. Log base 3 is a good choice. You can use any log you want. All right, I'm going to use log base 2. So we're going to take log base 2 of both sides. You have to use the same one because otherwise, right, if we don't do the same thing to the left as we do to the right, if we don't do the same thing, then it's not equal anymore. And we just changed the problem. You can't just ignore a problem or make the problem be what you want it to be. You have to deal with it as it is. So again, 2 to what power equals 2 to the x? And the answer is x. These are inverse functions. You're just left with that exponent. Or you could do it the long way like we did in the previous problem. Okay, the right-hand side is not so nice because these have different bases. But anyway, the right-hand side, the exponent still comes out in front. So you get x times log base 2 of 3. And now again, it looks kind of ugly, but it's still just a linear equation. Okay, there's no exponents. The only logarithm, this is just a number. There's no variable in here. This is just a number like x times 2 or something like that. Okay, so we get the x's on one side and then we're going to solve. Okay, so we need to subtract this over. So we get x minus x times log base 2 of 3 equals 0. And just like before, we're going to factor the left-hand side and then solve. Okay, so we factor out an x, just like in the previous problem. When we factor an x out of an x, we're just left with 1. When we factor an x out of this, we have minus log base 2 of 3. And now we divide both sides. You're going to get x equals 0 divided by this. Well, 0 divided by anything is just 0. This is our only answer. And this one is a much easier answer to check. Right? We can just plug this in and check. Not too hard. Right? If we check it, we get is 2 to the 0 equal to 3 to the 0. And yeah, they're both equal to 1. All right. This is the only place where these two exponential functions are equal to each other. And let's say you don't believe me. Let's say, Jason, you're a liar. You're a fibber. Well, I could argue with that, but I'm not going to. We can show this graphically, right? When are these two functions equal to each other? When is 2 to the x equal to 3 to the, oh, that's not a 3, that's an e. When is 2 to the x equal to 3 to the x? They have the same asymptote, but they never actually touch here. It looks like they touch. The only place they touch is right here, when x is equal to 0. And if you don't believe me, by the way, because again, it looks like they're the same thing here, let's just zoom in a little bit. There we go. See, oh my word, this hurts my eyes. See, this function is 0.0000004. This one is 0.0000978. So they don't actually touch. They look like they touch. But they don't cross. They only cross that once. Okay. I thought I would only have to zoom in a little bit. I had to zoom in a little bit more than I expected. They're pretty close. They're pretty close. But yeah, I'm glad you picked up on that, Lexi. All right. Let's do another one. Part G. G is in good. All right. All right, part G. What have we got here? 100 equals 20 e to the 2t. So this one's a little different. We could start by taking the log of both sides. And if you love logarithmic properties, be my guest. But it's a bit easier if you isolate the exponential first. And again, we say this all the time, and by we, I mean me. Me say this all the time. Isolate, right? When we solved square root equations, radical equations, we wanted the square root to be all by itself on one side of the equation. When we solve logarithmic equations like we did on Tuesday, right? We wanted the log to be all by itself on one side of the equation, right? So for when we did something like part B, we moved the 3 over, we divided by 2 because we wanted this log by itself. So frequently, when we solve a certain type of equation, we want to get that thing by itself, okay? So it's easier if you get that exponential by itself, so divide by its coefficient. Let's divide both sides by 20. Yeah, it's a great time for isolation right now. Treat that exponential like someone with the coronavirus. We're going to isolate it. Quarantine. Here, we should change the language. Quarantine the exponential. Okay? So we divide both sides by 20, and we're going to get 100 divided by 20 is 5, equals just e to the 2t. And now the exponential is all by itself. Okay? And now it's just like the previous two parts. So you can use any log you want, as long as you use the same one on both sides. You could use log base 2, you could use log base 5, you could use log base 7. But there's a really natural choice here, and that's to use log base e. That'll make things a little nicer if you use log base e. And remember, log base e is natural log. Why don't we use the e log? Great question! Yes, that's what we're going to do. I understand that you typed that before I said it. There's a small amount of delay, like 2 or 3 seconds, between when I say something and when you hear it. But yes, excellent, Delaney. So let's take the natural log of both sides. So we get ln 5 equals ln of e to the 2t. And we'll be good to go. The natural log of 5, that's just a number. We'll keep that as natural log 5 for a bit. But the right-hand side, log base e of e to something, these are inverse functions. They cancel each other out. The right-hand side is just 2t. Just like on your exam, right? On your exam, you had a problem, the natural log of e to the 1/3. Many people, not everybody, but many people, most people got this one. This is the same idea here. Okay? And we're solving for t. This one's even easier. Divide both sides by 2 and we're done. Now be very careful. Okay? You're walking down a dark alley in the middle of the night in a seedy section of Chicago. Okay? And I'm going to warn you and keep you safe. When you divide by 2, be very careful. This does not become 5 halves. This 5 is stuck in the natural log. This 2 is outside of the natural log. There's no combining them. Okay? So we get t equals the natural log of 5 over 2, which is our final answer. Why would we be doing that? You're the one there, Delaney. Why are you in seedy Chicago? Lexi, you too. You should know better. And this is the warning. They don't combine. My non-mathematical warning is don't do that. Okay, good. We're going to do one more that's similar to G, and then we're going to get on to some spicier problems. Okay, so part H is going to be 4 e to the 2x plus 5 equals 12. And so we're gonna take our lesson that we got from G. We're gonna take what we learned from G. Okay. I didn't eat broccoli. Do I actually have something in my teeth? I might. So we're going to do exactly what we did in the previous problem. Isolate the exponential. So what do we do to isolate the exponential? I think it was the skin from an almond. Subtract 5. Good. Good. No, I actually did have something on my teeth. No joke. I actually did have something. I was surprised that you could see it, but there was something there. Apparently you couldn't see it, but either way. So yeah, subtract the 5. We're isolating the exponential. So subtract 5 from both sides. So we get 4 e to the 2x equals 7. And then we say, that's not isolated. We divide both sides by 4. So we get e to the 2x equals 7/4. And then we say, okay, the exponential is isolated. Let's undo the exponential with its inverse. The inverse of e to the x is natural log. So we're going to natural logigate the whole thing. Okay? So, natural log of e to the 2x equals the natural log of 7/4. And remember, if we wanted to, we could split this up. This could be the natural log of 7 minus the natural log of 4, but we don't need to. Okay? These are inverse functions. They cancel each other out. Yeah, quarantine. We get 2x equals ln 7/4. And again, we divide both sides by 2. But you're going to be very careful. You're going to be very diligent. You're not going to be caught in seedy old Chicago. You're not going to make the mistake. It's the natural log of 7/4 divided by 2. The 2 is stuck outside. Okay? And that's how you do the first third of today. We have 2 more thirds to do. The next one is really, really where things start to get juicy. If you're thinking to yourself, Jason, I want some more exciting problems, you're about to get some. So let's go into part I. Part I as in I love this stuff. Okay. E to the 2x minus e to the x equals 56. Okay, so you say to yourself, I've been a good student. Oh my word, look at my camera. Say to yourself, I've been a good student. I've been paying attention. I need to isolate this exponential so I can natural log both sides. That's almost always the right choice. But right, if you isolate this guy, you move this one over to the other side, and then you have to take the natural log of something really, really messy that's basically impossible. Basically impossible is not good. So I'm going to make the impossible possible. Okay? There's a little trick we can do this thing. So notice. Right? E to the 2x is equal to e to the x squared. Everybody agrees with this. Under penalty of death. Everyone agrees with this, right? Because exponent raised to an exponent, you multiply those exponents. You get. So notice that this thing is just this thing squared. So we have a linear term. We have a quadratic term. It doesn't look like it, but this is a quadratic equation. Okay? So we're going to do some magic. Okay? So, let u equal e to the x. We're going to use a substitution. Cat hair is getting all over my face. So if u equals e to the x, what do we have here? U squared, right, is e to the x squared, which we just said is e to the 2x. So e to the 2x, this becomes u squared. Minus e to the x, we said that is u. And you may not be able to solve this, but I know you can solve this. Just a little bit of magic, a little substitution, and it's solvable now. Beautiful, right? Clever, neat. So we say, okay, we can factor this, we can use a quadratic formula, we can complete the square. One of these days, these cats are just going to get shaved, and I don't have to worry about cat hair in my face. We're going to try to factor this. U squared minus u minus 56 equals 0. We need something that multiplies to negative 56, that adds to negative 1. And I trust that you guys can factor things eventually. So I'm just going to tell you the answer. It's going to be 7 and negative 8. Yeah. So we get u plus 7, u minus 8. You're always going to use this. You can use any substitution, but this is the substitution that's going to make things possible. The idea is that you want to use this substitution so that you get a quadratic. Good question, though. And then just be very careful when you finish this problem, because, right, u is negative 7 and positive 8. Don't box this. I don't care what u is. I care about all of u, but I do not care about this u. Okay? The problem didn't even have u. The problem is asking, what is x? U is not important. X is, okay? So, we need to solve for x. Anytime you use substitution, you have to substitute back. All right? So we know that u is negative 7, and we know that u is 8. But again, we don't care about u. We care about x. So we got to go backwards now. We have to undo the substitution. Substitution was useful in getting to our answer, but now we have to get that good answer. Okay? So, what is u? U was e to the x. So we replace the u with e to the x. So we get e to the x equals negative 7, and e to the x equals 8. Right? It's like it's easier to work with it in use. Like, you could factor this. You could have factored this without any substitution. But most people are going to be much better at factoring this than they would be at factoring this. Okay? Right? It's kind of like, this is maybe a bad metaphor, but it's like if I ask you a question in Italian, maybe you're not so good at coming up with an answer in Italian. So what are you going to do? You're going to translate to English. And then you're going to answer in English, but then you have to translate back to Italian so that I can understand you. That's essentially what we're doing. We're doing all the math in an easier form, but we still have to answer in the right language. But it makes it easier to do the math when we don't have any exponentials. Okay, so we just finish. How do we solve this? We take the natural log of both sides. So we get the natural log of e to the x equals the natural log of negative 7. Ooh. And the natural log of e to the x equals the natural log of 8. Yeah, exactly, Lexi. Good. Good. So your heart should start to beat quickly now. Domain. Jason's been talking about domain all semester. What is he talking about domain for? Domain's all the x's that you can plug in. We say that the domain of a natural log, of any log, is positive numbers. We can't plug negative numbers into a natural log or any kind of log. When you type this right-hand side into your calculator is going to get very grumpy. And if you're not nice to your calculator won't be nice to you. Please do your part to prevent the robotic uprising and be nice to your calculator. It would be very unhappy. This does not exist. Okay? So this left-hand side has no solution. But it's okay. We'll get an answer from this one. So natural log of e to the x simplifies to just x. We get that x is the natural log of 8. And that is our answer. So these ones are, trickier, of course. So watch out for these. If they're both no solution, then there just will not be any solution. So, for example, if they both had a solution, then we'd box both. If only one has a solution, we only box that one. If neither of them have a solution, then we say, yep, there's nothing. Okay? Good stuff. All right, we're going to do another one of these. We're going to do another one of these, and yeah, it took like a full page. But attendance time. A good attendance question. How about I don't know. I don't think of any good attendance questions. Would you rather fight a horse-sized termite or a termite-sized horse? What would you rather fight? A horse-sized termite or a termite-sized horse? That'll be the attendance question for today. Okay? We can use Gabe's on Monday. All right, mine's a very important question. Fighting a termite-sized horse or a horse-sized termite? I think there's an easy answer to this question, but I'm not the most creative. All right, let's move on to part J. Part J is in jalapeno. Goodness, we're using so much paper today. All right. Part J is a good one. E to the 2x equals e to the x plus 2. And you say, whoa, Jason, this one's just like part I. What's with all the fighting today? I'm feeling violent. This one's very similar, right? We can't just natural log both sides. Right? Because if we tried to natural log both sides, we get the natural log of e to the 2x. Oh, that's nice. We'd also get the natural log of e to the x plus 2. And there's nothing we can do with this. Okay, so that's why we have to use a substitution. This is going to be a quadratic. This is going to be factoring. Okay. So, again, substitute. So just like before, u is going to be that e to the x. And just like before, u squared is e to the 2x. It'll always be this way for these substitution problems when they're quadratics. Yeah, maybe I get angry after grading. I hate grading. All right, so what do we have? U squared is e to the 2x, so just replace it. U is e to the x, just replace it. And then we'll go factor. Okay, so we get u squared minus u minus 2 equals 0. Let's say you didn't want to factor. Let's say you couldn't factor. We can. If you couldn't factor, you'd have to use a quadratic formula. I want to show you. What does that look like? Everyone loves the quadratic formula. You love quadratic formula. What happens if we use a quadratic formula? Well, we get u equals, and again, it is u. U is our variable here. U equals negative b plus or minus square root of b squared minus 4ac all over 2a. And we'll just plug that in and do it step by step. B is negative 1, so this becomes a positive 1. Plus or minus the square root of negative 1 squared is again positive 1. Minus 4 times a, which is 1, times c, which is negative 2. All divided by 2 times a, which is 1. And then again, you just simplify it. Your calculator can help, but be very careful when you use it. This becomes a positive 8, so we get the square root of 9, which is 3. So you get 1 plus or minus 3 over 2, and now we just split this up. So we get u equals 1 plus 3 is 4 over 2, which is 2. 1 minus 3 is negative 2 over 2, which is negative 1. So if you want to use a quadratic formula, you can. Just be a little careful. But then again, if I'm asking you a question in Italian, give me an answer in Italian. I want some pasta now. Okay? So let's continue on with the problem. U is 2 and u is negative 1. But remember, u is e to the x. So we get e to the x equals 2 and e to the x equals negative 1. We have to solve both of these equations. So again, we just natural log both sides, just like before. Natural log both sides, just like before. Negative numbers are not in the domain of the natural log of x. We can only put positive numbers in natural logs. This one is no good. Cannot take the natural log of a negative number. I believe there's some stuff in complex analysis that lets you do it with complex numbers, but I'm not familiar with it. So natural log of e to the x is just x. We get x equals ln2. What a cutie little answer. Cute little answer. I made a second column, but we didn't even need it. We finished the whole problem in one page. Whoa! All right. So if you get problems like this with that e to the 2x and an e to the x, if you have multiple exponentials like that and you can't solve for one of them, you can use the substitution here. Otherwise, just try to get one of the exponentials by itself and log both sides. All right. Essentially 2.5 problems left. Applications. So, part K. Part K as in example 3. Because it's not part K. Okay. Radioactive decay. Oh, radioactive part decay. All right. So there's two formulas that model radioactive decay. A of t equals a naught, or a sub 0, e to the negative kt. Sometimes you may also see a of t equals a naught, e to the natural log of 0.5 divided by capital T times little t. And don't worry, I'm going to pause soon and not overwhelm you. This capital T, this is called the half-life. A sub 0 is the initial. Okay, let's talk about this. Let's talk about this before we do the example, because there's a lot going on here. And why don't we zoom, get super zoomy? Okay, make it nice and big. Okay, so let's calm down. Calm down. So what do we know about exponential functions? Let's forget about radioactive decay for a bit. What do we know about exponential functions? We said exponential functions are always of this form. Well, they can be of this form, where this is our initial amount, this is our growth or decay rate, and they have an exponent. Well, they can also look like this. Okay? So these are the same function. The only difference is that here is our k. We have a negative k like this. It can also be expressed like this. This is a simpler function. So you need to know what is half-life. What the heck does a half-life mean? If you know what half-life is, you just plug things in, and you're going to be okay. All right. So when we have radioactive decay, a half-life just means how long does it take for half of the substance to decay. Okay, So let's say that we're looking at a box full of material, right? Then after one half-life, we have half of that material left, right? Half of it decays. After another half-life, another half decays, right? And then after another half-life, another half of the thing decays. Okay, so that's what half-life is. This is just a time. The time it takes for half of the material to decay. Yeah, you'll use a calculator for this for sure. And conceptually, it's nice when you know what a half-life means, but it's not completely necessary. Okay. So example 3, I should have mentioned this before example 3. We haven't even started example 3 yet. This formula will be given to you. You do not have to memorize this formula, just like with compound interest. You just have to know how to use the formula. Okay. So what do we have? We have a question. Example 3, part A. Let's zoom out a little bit. Part A. How long will it take until 30% of a 1,000 gram sample of uranium-235 to decay? The half-life of uranium-235, I believe this is the abbreviation for that, is long. The time, half-life, right? Time it takes for half of this material to decay. That half-life for uranium-235 is 703.8 million years. So it's going to take a while. A long time. Guarantee you, you stare at that uranium-235, you're not going to see very much decay. All right. And it's probably not good to be around. Oh, no. This is just notation for an isotope. An isotope of an element is an element with just an irregular number of crap. It's an irregular number of protons, right? Oof, it's been a while since I took chemistry. It's not subtraction, though. It's like, it's just a dash. It's like part of the name. And this right here is shorthand. It's not an exponent. Okay, so another thing that you'll see a lot is like carbon-14. When you see carbon-14, you're going to see it written as carbon-14 like this. Or sometimes you'll see it written as carbon-14 because C is the element carbon. More neutrons than protons. Oh, okay, thanks. Because that's what we're dealing with here. This is just how you write isotopes. Good. I'm learning stuff today too. All right, so we just use a formula. Okay, so it looks super spooky. But what is A of t, right? What is A of t? Well, I have to zoom out a little bit so we can see it. A of t is equal to A naught, A sub 0. We said that's the initial amount. How long will it take till 30% of this has decayed? This is our initial amount, 1,000 grams, 1 kilogram. Times E raised to the natural log of 0.5. You can't see it, but it's there. Divided by T, our half-life. The half-life is 703.8 million years. So, do you want to write 703.8? Or do you want to write 703 million years, 800,000? It's up to you. Just remember what you choose. I'm going to have everything in terms of million years times T. This is our formula, plugging in everything we know so far into here. That's our A of T. And the question is, how long is it going to take until we only have, wait, hold on, there's a typo. How long will it take until 30% remains? That was terrible English before. Okay. E is Euler's number. It's like 2.718, etc. We're going to set it equal to 30% of what we started with. So when does 30% remain? Well, 30% remains. Well, what's 30% of 1,000 grams? Right? Should be 300 grams. So we're really curious is when do 300 grams remain? So when is 300 equal to 1,000 times e to the natural log of 0.5 divided by 703.8 times t? We have an exponential equation to solve. All right. This is going to be a big portion of what we're doing in the final section on Monday. It gets a little messy. Remember the basics. Isolate, isolate, isolate. We want to solve this, so we're going to solve this by isolating the exponential. Right? Isolate the exponential means divide both sides by 1,000. So we get 300 divided by 1,000 equals e to all of this stuff. It's messy, but honestly, solving problems and solving actual real life problems with math is usually messy. And now we undo the exponential with its inverse function, the natural log. So we need to take the natural log of both sides. Also, fun fact, by the way, 300 divided by 1,000 is 30%. Not a coincidence. You don't like this? It gets better. It gets better. The more and more problems that you do this, it's like Stockholm syndrome, right? You're held captive by this problem, but the longer you're captivated by this problem, the more you're going to like it. So we need to take the natural log of both sides because we need to solve for t. We need to undo that exponential. So we get the natural log of the left-hand side, which is again just 3/10, equals the natural log of the right-hand side, which, is going to be a big thing. But don't worry, it's not that bad. It's not that bad. I mean, it's kind of bad, but it's going to get better. It's going to get better. Because look at the right-hand side. We have the natural log of e to some power. These are inverse functions of each other. Boom, inverse functions cancel each other out. We're just going to be left just with the exponent. It's a big exponent. That's all we're left with. We get the natural log of 3/10 they cancel, is equal to the natural log of 0.5 divided by 703.8 times t, and you're almost done. Okay. This is our variable. All we need to do to finish is multiply by the reciprocal of the coefficient. We want this t by itself. So to undo this fraction, we multiply by its reciprocal. So on the right-hand side, we multiply by 703.8 divided by ln of a half. On the left-hand side, we multiply by 703.8 divided by ln of 0.5. And then, right, they cancel. And we're left with t is equal to this left-hand side. But this is an application problem, so we're going to approximate, okay? We'll type that left-hand side into our calculator. We type in, what is 703.8 divided by the natural log of 0.5 times the natural log of 3/10. And the answer is 1,222.5. And remember, what is t? We said t was in millions of years. So it's going to be a long time till this decays. If you wanted to answer also 1.2225 billion years, you could as well. Wow, what a problem. That's a long time. All right, uranium-235 does not decay very quickly. All right. It's going to take a while. Two more problems, and then we'll be done for the day. The last one's a good problem. Part B, again, you're probably going to be a little unhappy with part B. But the next problem will be a good one. Example 4. The uranium killed you? Yeah, maybe. All right. Let's do part B. Again, I'm just going to rewrite the formula so we have it as reference. A of t is a naught, e to the ln 0.5 divided by capital T times t. Part B. How long until 10% decays? So I really wanted to do part B because it's different phrasing. The most important thing in part B is how long until 10% decays. If 10% decays, this is the most important part right here, right? If 10% decays, we have 90%. Okay? So you're not putting anything with 10% on the left. We're wondering, when do we have 90%? It could be a short day. I could go through these problems faster if you wanted. But yeah, I didn't say Friday was going to be a short day. I said Friday might be a short day. But I also said it was going to be full of some interesting questions. To be fair, yeah, maybe I lied. Okay, so if you wanted to put this as 2,000 grams again, or 1,000 grams, and if you wanted to put this as 90% of that, you could, but there's a little shortcut you can also take. Let's not take shortcuts right now, though. Okay, so again, initial is 1,000 grams, and we're curious about when we have 90% of that. That's 900 grams. So we just solve it just like before. Just like before. When is 900 equal to 1,000 times e to the natural log of 0.5 divided by the half-life, same half-life, is 703.8 million years times t. And you just solve this the exact same way that we solved the other one. Upon request, here's how you solve it. 900 divided by 1,000 is 9/10 equals e to the same thing as you had up here before, divided by 703.8 times t. Take the natural log of both sides, you get the natural log of 9/10 equals, they cancel each other out, the natural log of 0.5 divided by 703.8 times t. Multiply by the reciprocal, you get t is going to equal the natural log of 9/10 times 703.8 divided by natural log of 0.5. Type that into your calculator, and you're going to get approximately 107 million years. No. You guys said go faster. That's what I heard. I heard, Jason, you're going too slow. I heard, Jason, this problem is too easy. Speed it up. We don't want to be here all day. So, same steps. In fact, all of these problems, once you set them up, these are always going to be the same steps. All right. So look back at your notes when you're going through this homework assignment. All right. And we'll do a little bit more of this on Monday. All right, we got the last problem of the section. We'll go normal speed for the last problem. Last problem of the section. Example 4. This is a fun problem. You, right there, you invest, let's say, $150 with 3% interest, compounded continuously. Question is, when will you have $200? So recall, A of t equals A naught e to the RT is our formula here. Don't put a dollar sign in your answer here. When are you going to have $200? Delaney says after $5. No, don't do that. But yeah, don't forget your units. Okay. So we're wondering, when do we have $200? That's when the amount is $200. We start with 150. Our interest rate is 3%. And remember, 3% is a decimal. 0.03 is what we plug in. Okay? Do not plug in 3 here. That would be a 300% interest rate. So please remember, decimal. We are using the other equation, Lexi. This right here is the other equation for compounded continuously. There was a second formula for compounded like monthly, annually, semi-annually, but there were 2 formulas. But this is the one that you did. Maybe it had a different letter here. Was it a different letter here? But it should be the same formula. And then we're asking, when do we have 200? So that 200 becomes the left-hand side. And we're solving for t here. So to solve an exponential equation, oh, it was p. You're right. To solve an exponential equation, isolate the exponential. So you need to divide by 150. So we divide by 150. The exponential is isolated. We can natural logarithmicize both sides. And we can also reduce. This is 4/3. So we get the natural log of 4/3 equals the natural log of e to the 0.03t. And again, these are inverse functions. They cancel each other out. We're just going to be left with that exponent. We're almost done. We get the natural log of 4/3 equals 0.03t. If we divide both sides by 0.03, we'll be good to go. And you get that t is equal to the natural log of 4/3 divided by 0.03, which is approximately something. $9.589, or about 9.59 years. And that's a decent answer. But really, we don't talk about decimals of a year, right? So you can kind of convert that. What is 0.59 years? Well, a year is 12 months, so 0.59 years is about 7 months. So about 9 years and 7 months. Because 0.59 years is about 7 months. This is a better answer. But I'll take either. Okay, great. So that section's over with. You can have a nice weekend working on the homework. 6.6 is a good section. And a little bit of a warning. I'm going to warn you while you're out walking in a summer field with beautiful flowers and cute fuzzy dogs, if you like dogs. Watch out. If this section's tough, Monday is going to be rough. Okay? So spend some time over the weekend if you can. Look at some homework problems, get a little bit more comfortable with this, because Monday is going to come fast and Monday is going to come hard, and Monday's a good section. Monday's an interesting one. Okay, so yeah, that's what we've got coming up. Have a good weekend. Monday, we're starting the section. Tuesday, we're finishing the section, probably. Wednesday, we'll finish the section if we need it, and we'll do some review. Thursday's your final. Goodbye.